Hey everyone, today I'm going to talk about our work on robustness of machine learning models for ad and tracker blocking. And this is joint work with Umar Iqbal, Stephen Englehardt, Zubair Shafiq, and Carmela Troncoso. So nowadays there are a lot of blocking solutions that are aimed to address the issues caused by the online advertising and tracking industry. Now, many of these blocking solutions rely on manually curated filter lists. So here on the slide, I have an example of what I mean. So let's take the AdBlock Plus extension. It uses a filter list called EasyList, and I've shown a couple of rules in this list and what they look like in the snippet there. The idea is that once you have a page load, the resources on the page are matched against the rules on the filter list, and then they're blocked or hidden based on the rule. Now, the manual curation of these filter lists has two main issues. One is that it's hard to keep these filter lists up to date with the constantly evolving ad and tracker ecosystem. Prior research has shown that it can take up to 3 months to add a new rule to the filter list, and that majority of the rules are now no longer applicable to ads and trackers that are existing at the moment. The other issue is robustness. Since these filter lists are working on pattern matching, ads and trackers can employ techniques such as URL randomization in order to evade these patterns, and thus these filter lists are no longer useful. So keeping these issues in mind, the research community has been looking towards building automated detection systems that are based on machine learning. Now, the previous automated detection systems looked either at the network layer features of ads and trackers such as URL or HTTP information, or they looked at the JavaScript activity by performing static and dynamic code analysis. But the latest approaches for automated detections argue that ads and trackers actually work across all the layers of the web stack, and so we should be going for a cross-layer approach that combines interactions across all of these layers. So I'm going to talk about the first main cross-layer approach, which was AdGraph, and I'm going to use this as a representative example of all the cross-layer approaches we have today. So what AdGraph does is it builds a graph representation of all the page load events that occur, where the nodes in the graph are the different kinds of elements that are there on the page, and the edges between these nodes represent various interactions between these elements. So you can have events which are normal and like required for the functioning of the page, such as loading a style sheet or an image and so on. But you can also have tracker events, and these look different from normal events. And the idea behind these cross-layer approaches is to find these differences between tracker events and normal events and use that to identify ads and trackers. Now, all of these approaches so far have been shown to have good performance. They identify ads and trackers with high accuracy, but we were interested in studying whether they're actually robust to adversarial evasion. And I'm going to explain what I mean by adversarial evasion in our scenario. So let's say that you have a site that you're visiting, example.com. This site would consist of resources that belong to the first party and the third party, where first party resources are those that share the same top level domain as the visited site, and third party resources are those that have a different domain. So let's say that AdGraph is running, and then it classifies some of these resources as benign and some of these as ads and trackers. The adversary in our scenario is a third party that aims to get its ads and trackers misclassified as benign content. Now, what AdGraph does is it builds a graph representation, and then it extracts a number of features which it then uses to train a machine learning model. And the features can be broadly categorized into two. We have content features that are related to individual nodes in the graph, such as URL or HTTP information. And then you have structural features which are related to interactions between the nodes, such as the degree of a node or the connectivity and so on. And what we observe is that actually the content features are pretty easy for an adversary to manipulate. So this leads us to our first research question, which is how much do these graph-based detection systems rely on content features? In order to evaluate this, we took a set of 10,000 pages. We ran AdGraph to classify all the URLs on the page as benign or adder tracker. And then we performed content mutation, which consists of domain name randomization and query string randomization. And then we ran AdGraph again to see how the classifier's predictions change on this mutated data. And we evaluated this under 2 collusion models, one where the third party does not collude with the first party, and the second one where the third party has limited collusion with the first party. That means that the third party can become a subdomain of the first party, and this is nowadays possible via techniques such as CNAME cloaking. And what we look at is the success rate of the adversary, which is what I show on the x-axis here. And the success rate is basically the proportion of the ads and trackers that the adversary is able to get misclassified now by the classifier. And we see that the average success rate is very high, especially in the collusion model. We get it around 96%, and about a third of these mutations actually happen to URLs belonging to ad exchange trackers, which is even a greater impact for user privacy because these ad exchanges can diffuse user information further into the tracking ecosystem. And when we look at the features of AdGraph to see why we get such a high success rate, we see that the top 3 features that AdGraph uses are related to the content, that is like URL characteristics, and mainly whether a particular URL is a third party or not. And what we conclude is that AdGraph and related ML-based approaches actually fall prey to the same issues that filterlists suffer from, and that is that they rely on these brittle content features which are quite easy to evade. Now, when you look at the original performance in terms of accuracy of AdGraph, you see that it's about 92%. And now, if you decide to remove the content features in order to improve the robustness, you see that this results in a hit to the performance of the classifier, and the accuracy drops to about 80%. So this was our next research question, which is, can we actually improve the performance of these graph-based detection systems without using these brittle content features? And the main sort of insight that we had is that these graph-based detection systems, they have features related to what ads and trackers are, which is what the content features represent, but they don't have many features related to what ads and trackers do or their behavioral information. And especially in the kind of tracking that we look at, which is stateful tracking or tracking via identifiers, ads and trackers primarily do 2 things. Ads and trackers have to have some access to storage, such as cookies or local storage, in order to store identifiers. And ads and trackers often share a lot of user identifiers with other parties in the ecosystem using techniques such as cookie syncing. So keeping these things in mind, we created our system WebGraph, where the idea is to capture these fundamental patterns of tracking behavior, because these behaviors are very difficult for ads and trackers to hide. And we do this by performing 2 things. We augment the graph structure to take into account tracking behavior, and we introduce a new category of features based on our augmentations called flow features. And I'm not going to go into the details of how we make these enhancements, but I just want to illustrate what we mean. So let's say that we have AdGraph's representation of some tracker events, and this looks like this as I show on the slide. With our enhancements, we actually see that previously disjoint tracker events are actually quite connected through common accesses to storage or sharing activities. And for WebGraph, we completely get rid of the content features, and we introduce a new category called flow features, and these could be things like how many times a particular cookie is modified or accessed, or how many times a cookie value is shared with another tracker. And what we find is that with the structural and flow features, we don't actually get back to the original performance of AdGraph because the content features do provide some value, but we are able to make up for a lot of lost ground. And more importantly, when we perform the same content mutation against WebGraph, we see that the success rate of the adversary drops from 96% to about 8%. Now, we were interested in exploring whether WebGraph is actually also robust to an adversary that specifically targets the features that WebGraph uses and which we can envision adversaries to use in the future to evade these kind of systems. And I'm going to illustrate what I mean with a toy example. So let's say that we have a site, and this site is composed of resources belonging to the first party, the adversary, which is a third party, and other third parties. Now, WebGraph would have classified some of these resources as benign and some of them as ad and tracker. Now, what the adversary could do is perform some kind of a graph mutation. Here I'm just showing one example, but please read our paper to see other realistic examples of mutations that an adversary can create. So here the adversary adds a child node by sending an HTTP request. And what happens here is that the adversary's structural properties actually change, like the degree of the adversary now changes, and these kind of changes can trigger misclassifications by the classifier. But the problem is that now, since all the nodes in the graph are actually connected, structural properties of the other nodes that do not belong to the adversary would also change, and some of these misclassifications can be desired from the adversary's point of view, but there can also be misclassifications that are undesirable. So what we have now here is, on the x-axis, we have the success rate as before for the adversary, but now we have a new property here called the collateral damage, which shows the proportion of undesirable changes from the adversary's point of view. Now, ideally, the adversary would like to be in the bottom right corner of this plot, but we see that not only is the adversary not always able to get a high success rate, but oftentimes the collateral damage is also non-zero. So what we want to say is that these kind of attacks can be successful if the adversary is willing to tolerate these kind of side effects, but more importantly, in reality, implementing these attacks is not very easy. A lot of the features that WebGraph uses are things that involve sharing of information with a bunch of different parties. So to change these information sharing patterns, in reality, the third party would have to coordinate with a number of entities and completely restructure how they share their data. So in short, what we found is that the current graph-based detection systems are relying too much on these content-based features, but in reality, we should be looking at tracker behavior, and these can make the graph-based detection systems a lot more robust to adversarial evasion. Thank you.